In this problem, we're going to take a look at the forces that act between charged particles in a quantitative way. In a qualitative way, in the lab, we saw that opposites attract and likes repel. But here we want to take a look at how much force in newtons is actually acting on these charges. So I'm going to take two charged objects. I'm going to have two positive charges here. And since they're both positive, we know that they're going to repel because likes repel. And so I can just qualitatively look at this and say that there's going to be force acting this way on this guy, and equal and opposite force acting on this guy because they're going to repel. And if we had opposites, then they would be attracted, so the force vectors would point inwards. Okay. For this one, I'm going to say the charge is, now charged, we use the variable q. I'm going to say the charge on particle 1 is 4 times 10 to the minus 6. Minus 6, and the unit for charge is a C for Coulomb, named after Charles Coulomb. C stands for Coulomb. And the charge in the second guy here, I'll call Q2. Q is the variable. I'm going to say it's 5 times 10 to the minus 8. So these are little small particles with really small charges, as you can see with the exponents, minus 6 and minus 8. Minus 8 coulombs. And I'm going to say that these two charges are 3 meters apart. So they're kind of far apart here. And I'll use their centers as the reference, how far they are apart here. Because as you saw in the lab, how far the charges are away from each other determines how much force. The closer they are, the higher the force. So we want to find this force. What's the force actually acting on these things? So for charged particles, we have a new equation called the Coulomb's law equation. And it looks like this. It looks like K, which is a number, which I'll show you, times Q1, that charge we saw, times Q2, divided by the distance between them squared. Okay, so the magnitude of the charges Q1 and Q2 that are given here, K is a constant, and we're going to divide by the distance squared. So let's list our variables here. F, which we're trying to find, we don't know, but it's going to be in newtons. And this is, let's see, K, let's write down K here. Q1, Q2, and R. Okay, so K is a constant, and that number is actually a pretty large number. It's 9 times 10 to the 9th, and the units are newtons, meters squared, over coulomb squared, and we'll see how the units work out here in a little bit. Q1 is that charge in the first guy, so that's 4 times 10 to the minus 6 coulombs. And the Q2 is 5 times 10 to the minus 8 coulombs. And these are really small charges, but these are typical of charges you'll see like in things that are statically charged. And this is 3 meters apart. Okay, all right. So force we don't know, we're trying to find it, and that's the unit of newtons when we do get it. So that isn't changed. Force is still the newtons. This is a constant K. There are two charges and the distance between them. So if you plug in the numbers here, so algebraically it's pretty straightforward. It's going to be 9 times 10 to the 9th, 4 times 10 to the minus 6. So make sure in your calculator we're entering the exponent incorrectly. And this is 5 times 10 to the minus 8th, divided by the distance between the two charges squared, so 3 squared. So if you do the math here, I get an answer of 0.0002 newtons. So it's a pretty small force there, okay? But, and that's your answer, so box that answer. Okay. So that's a pretty small force there, but these charges have really low mass, so even though the force is small, they have really low mass, so they could be moved relatively easily by that small force. And if we were to bring them closer, if I were to decrease this number from 3 to 2 or 1, the force would get even bigger. So we have a larger force as you get closer. One last thing, take a look at the units here. We have this kind of a weird unit here for this newton meter squared. So if I take a look at the equation here, from a unit standpoint, this K is a newton, and the units are meters squared over coulomb squared, which is an interesting unit there. The units for charge are coulombs for the first guy, and coulombs for the second guy. And then on the bottom here, R is meters, so it's meters squared. So if you take a look at this from a unit standpoint, I have a Coulomb times a Coulomb, which is Coulomb squared, so that cancels this guy here. And I have a meter squared on top and a meter squared on bottom, so that cancels there. And the unit that I'm left with is a Newton. So the bottom line is, if I make sure that my units are coulombs for charges and meters for the distance, then my final unit here will be a Newton, which you can see right there. So this is a quantitative example of Coulomb's law, where I had to solve for force, but given any one of these variables, any one of these are missing, if I'm given the rest of them, I can solve for any other quantity.